Welcome to Chapter 9, Part 2. In this video, we're going to cover calorimetry. This is the topic of Experiment 11 in lab. We are going to be talking about the qualitative measurement of heat flow. We're going to learn several new equations, and we are going to attack some different problems using those equations. But first, let's jump into some definitions. When it comes to measuring the flow of heat into and out of a system, it's important to recognize that different materials will absorb or release different amounts of energy based on three main things. The amount of material, so that could be in mass or in moles. The type of material, and that's where heat capacity is going to come in. And then the temperature change that we are wanting to impart or that is observed. So heat capacity itself is the amount of heat that is needed to change a substance by a degree. Heat capacity on its own isn't super useful because it, of course, changes based on how much material you have. Changing a gram of water or, let's say a milliliter of water, 1 degree is going to be much less than raising the temperature of a lake by 1 degree. So what can be more helpful is something like specific heat and molar heat, which takes kind of a ratio, and so you can actually compare different substances. So let's get in here and look at this. You've got the definitions over here on your slide. Specific heat is abbreviated with a lowercase c, and it is the amount of, it is defined by how much heat is needed to heat 1 gram by a certain amount of change in temperature, right, by 1 degree. So to determine C, you would take the amount of heat that flows in, divided by the mass, and the change in the temperature. The equation that we are going to find more useful, that you're going to see on your formula sheet, that you're going to see in the slides, is just a rearrangement of what we just wrote here, and that is the amount of heat is equivalent to mass times specific heat times delta T. It's going to be important. We're going to use that equation a lot today. The molar heat capacity is the same idea. It's capital C sub P. Sometimes you'll see capital C sub M. It just depends on where the problem's coming from. But this is going to be the amount of heat that is necessary to raise the temperature of 1 mole by 1 degree. So you're going to see N instead of M. N, if you remember from your gas laws, is going to represent moles. You can also rearrange this one to get Q equals N Cp delta T. Now, these are the equations that we are going to be manipulating, talking through calorimetry, and working through these next couple of problems. Something that we want to discuss here for just a moment, though, is delta T. We're going to make a note on delta T. Delta T can be in Kelvin or in degrees C, and it doesn't matter. You do not need to convert when it is delta T. Now, why is that? Let's think about a system that goes from 20 to 30 degrees C. Right, so this is Celsius, this is Celsius. Delta T would be final minus initial, and it would equal 10 degrees C. Well, let's convert those to Kelvin. 20 degrees C would be 293 Kelvin. Going to 30 degrees C, or 303 Kelvin, that would give us a delta T of 10 Kelvin. All right, so delta T does not need to be converted. You do not convert delta T. Why is this so important to note? Well, sometimes we are going to come across tabulated data, and the units of specific heat are joules per gram Kelvin or gram Celsius. You may see it as gram Kelvin or gram Celsius, and it simply doesn't matter because it's delta T. Same over here for molar capacity. Let's keep that in mind as we look at our first problem. So on the next slide, you have this problem. You also have it written out in your notes here. We are heating an aluminum can there we go, a 24-gram aluminum can. So we know our mass. We want to raise the temperature, so it's a positive delta T, right? Final is going to be greater than initial. So we are raising it 15 degrees C. We want to find Q, so the only thing that we're missing is C, is heat capacity. The reason it's not given in the question is because it was on the previous slide. It would be given to you in the question. You do not need to memorize this number. C is 0.900 joules per gram Kelvin or gram degrees C. Right? It doesn't matter there. So now we can just plug and chug. If Q equals MC delta T, we just plug in the 24 grams, the 0.9 joules per gram degrees C, and our temperature of 15 degrees C. Right? We see that Celsius cancels out, grams cancel out. We're left with joules. We're left with joules here, and that's perfect because this question is asking for an amount of energy. When we complete this problem, we find that it takes 324 joules to heat this aluminum can by 15 degrees. Okay, let's do a practice problem with molar heat capacity. Now, I'm going to remove this slide because if you're working on a problem and you don't have all of these numbers memorized, I want to show you how you can handle having a molar heat capacity, but perhaps you are given a mass instead of moles. You guys already know how to handle this, but let's make sure together we work through a problem. So in this problem, we know the molar heat capacity, right? So let's write this down. We have CP is 75.3, joules per gram Kelvin. We know that, or I'm just going to stick with degrees C because that will keep everything consistent. We know that we have a mass of 37.5 grams, and we know that our delta T is final minus initial. So in this case, final it's cooled from 42 to 7. So it's going to be 7 degrees minus 42 degrees, which is negative 35 degrees. All right, so it's always final minus initial. Now, when we go to set this up using CP, we know that Q equals NCP delta T. But we have mass, right? So we're going to need to convert, right? Q is going to equal 37.5 grams, but we're going to convert that to moles. You guys know how to do that with molar mass. There are 18 grams in 1 mole of water. I'll expand that a little bit. Right? So now grams cancels out and we're left with moles. Now we can plug in our CP, that's 75.3 joules per mole degrees C. We know the change in temperature is negative 35 degrees C. And now it's just a matter of plugging in, or a matter of calculating, right? Moles cancel out, degrees C cancels out. Again, we are left with joules, which is what we want. So when we solve for this problem, right, and account for significant figures, we're going to find negative 5,490 joules is our answer. All right, that is how much energy is released from this system. That's how much energy is released from 37.5 grams of water when it cools negative 35 degrees. All right, so that sign is also part of the story. Now, when we are doing calorimetry problems, heat flow is measured using a calorimeter. Because in most cases, you don't want to measure the entirety of the surroundings, right? Because the surroundings is the entire universe, and we can't really adequately respond to that in a small setting like a lab. So what we do is we try to limit what the surroundings are, the kind of the nearest surroundings that are going to be affected, and we do that with a different apparatus. But first, we're gonna look at a simplified problem to see how we can use this first law of thermodynamics, right? Whatever energy the system absorbs, that much is lost by the surroundings. However much is gained is equivalent to how much is lost. They'll be equal but opposite in sign, right? Because energy is neither created nor destroyed. So in this first problem, we're not going to think too hard about reality. We're looking at a glass of water, and in that glass of water, we're putting in hot metal, right? So there's going to be some gold placed in this water. The final temperature of the water is, of course, going to increase because you have this cold water, you have this hot metal, and energy is going to leave the metal and go into the water. What we're asking you to do here is assume that no heat is lost or gained from the glass of the beaker, the air in the room. It's not accurate, but it's going to make this problem a bit more simple to solve. And so it allows us to calculate what is the mass of the gold if we remember that however much energy, right, is lost by the gold, right, that is going to be how much is gained by the water. Right, if there's nowhere else for the energy to go, if it's just leaving the gold and entering the water, then the change in energy of the gold is going to be equal but opposite in sign for the change in energy of the water. Now, we have enough information. We have the mass of the water. We have the initial temperature. We have the initial temperature of the gold. We have the final temperature of both, right? That's going to be TF for both sides. We've got the specific heat of the water and the specific heat of the gold. So when we set this up, we're going to see that, right, Q, gold, is mass of gold. Actually, what am I doing? Mass of gold times the heat capacity of gold times delta T for the gold equals negative, right, opposite in sign, the mass of the water times the C of the water times the delta T of the water. Now, what are we trying to solve for? We're trying to solve for the mass of the gold. So let's rearrange this, and then we can just plug in, right? We know that mass of the gold will equal all of that for the water, MH2O, CH2O, delta T H2O, over CAU, delta TAU. That's a U. There we go. All right, it's just a little bit of rearranging, and now we can just plug in and solve. So the mass of the water was 250 grams. The heat capacity of the water is 4.184. Let's blow this up a little bit. Joules per gram degrees C. The delta T is 76.9 minus 78, right? Final minus initial. So, warm water and a piece of gold. Oh, okay. So we actually put, in this case, hot water, cold metal, heat's going into the metal and somehow not being lost by the glass. Sorry, I didn't recognize that until I saw the sign of our delta T. All right, so delta T here is negative 1.1 degrees C. On the bottom, C of AU is 0.129 joules per gram degrees C. And the delta T of the gold is going to be final, again, minus initial. So 76.9 minus 2.3. All right, so the change in temperature of the gold is a bit more significant. And what's that delta T? 74.6 degrees C. Now, once you set all of this up, it's just a matter of plugging it into your calculator. All of your units are going to work out here. All right, joules cancel out, degrees C cancels out. We wind up with, oh, sorry, the grams over here canceled out, not down here. We wind up with 1 over grams, and actually that is the unit that we're looking for. 1 over grams is grams. So we're going to just continue on our notes down here. And this is equal to 120 grams of gold. With keeping track of significant figures here, I'm sure. But this is our final answer. So this is how we could use calorimetry to solve for mass, right? When we've got both the system and the surroundings, right? It's a little bit more complex, but it's still just plugging and chugging at the end of the day. Now, calorimetry is typically a little bit more complex than that, because in that last scenario, we had to assume that no heat was transferred to the glass or the surroundings outside of the glass. When we actually do a calorimetry experiment in the lab, like you saw in experiment 11, we use styrofoam cups to help insulate. And then there's also something, and we'll come back to this page in just a moment. There's also something called a bomb calorimeter. This is especially useful when you're trying to figure out the energy content of a fuel or of a food. You can place your fuel in this inner chamber called a bomb. This is where you can ignite it, and then there is water. This is your surroundings, and you don't have to worry about that energy escaping into the universe, because there is a vacuum layer and then there's an insulated layer. So over here in a simplified version, right, the system is exothermic, you're burning something. Heat is going to go out into the immediate surroundings, that is the water, but they're not going to be able to flow further out of the calorimeter. So it gives you a kind of a smaller microcosm to analyze. It makes these problems have an extra step, so we're going to come back to this slide for just a moment. You have to calibrate a calorimeter, right? The heat capacity of a calorimeter, or C-cal, is Q over delta T, right? It's the amount of energy that it takes to raise the temperature of the calorimeter by some amount. But you notice there's no mass or moles here, because the calorimeter is an object. You are not going to have part of a calorimeter. You're going to have one whole calorimeter, and that calorimeter is going to have its own calorimeter constant. That is going to be important in solving this last problem here. Something that you want to be aware of. When you find the amount of energy that was absorbed by the calorimeter, it's important to recognize that is the amount of energy that was given off by the reaction inside of that little bomb, but it's going to be opposite in sign. Right? If the amount of energy if the water heats up, then Q-cal is going to be positive. That energy that it absorbed all came from the reaction, so then the Q of the reaction would be negative. What's important to recognize is that they are equal, but they are going to be opposite in sign. All right, so let's take that knowledge and let's move on to this last practice problem. We have a calorimeter, And with an electrical resistance heater, so this is a heater where we can control exactly how much heat is given off, right? So now Q is known and it's constant. And we can measure the temperature that the calorimeter increases. In this case, it's 0.85 degrees C. After we do that, we can burn our fuel. So before we even approach the second half of the question, we can figure out, oh, maybe we don't want a highlighter. Here we go. We can figure out C-cal. We know that when 100 joules of heat is applied, delta T, right, it increases, so it's a positive 8.5 degrees Celsius. So the calorimeter constant in this problem, is 118 joules per degree C. That's going to be useful as we continue on with this problem. All right, now we have our reaction. Our reaction uses 0.245 grams of fuel, 245 grams of fuel. We know that when it is burned, in the same calorimeter that we just calibrated, we know that delta T is 5.23 degrees C, right? That's of the calorimeter. The water goes up 5.23 degrees C. We want to calculate the energy density of this fuel, which is the amount of energy liberated per gram. So we want to find Q per gram. All right, so let's think about what we have here. We can figure out Q of the calorimeter in this experiment because we have delta T and we have C-cal. Right, that's going to be, if I rearrange this equation up here, I know that Q-cal equals C-cal delta T. So that would be 118 joules per degree C times 5.23 degrees C. All right, so the amount of energy that it took to raise that calorimeter, that 5.23 degrees, is, let's see, 615 joules. Now, that's how much energy was absorbed by the calorimeter. If we want to know how much, right, if the question was, what is Q of the reaction? Well, then Q of the reaction would be negative 615 joules, right? It depends on what the question's asking for. If you want to know how much energy was absorbed by the calorimeter, it's positive 615. If you want to know how much was lost by the fuel, it's negative 615. In the last question, it's not quite as important, the sign. The last question is how much energy per gram. What you want to recognize here is that this was the amount of energy for 0.245 grams. You notice we haven't used that number yet. If we want to convert this, right, so we're going to do our last little bit here, energy density. We are going to see that 615 joules is given off for every 0.245 grams. Now, if I just do that division, 615 divided by 0.245, that'll give me energy per gram. There is actually 2,510 joules released per every gram of this fuel. All right, now if you had a negative in there, that's fine. That's telling you that it's released. Essentially, you're more interested in the sign when you are dealing with Q-cal and Q reaction. That's what I really would like you guys to focus on. That's what you're going to need when you go into your lab, when you go into practice problems. There's a lot of homework problems with this as well.